It is 1964, and two grown men are on their hands and knees inside a giant metal horn on a hill in New Jersey, scrubbing it clean. They have taped over the rivets, they have trapped the pigeons nesting inside and mailed them away in a box, and when the birds flew straight back, they shot them. They have done everything a careful engineer does when a machine will not stop making a faint, maddening hiss that should not be there. And the hiss will not go away. What Arno Penzias and Robert Wilson do not know, what they cannot know yet, is that the sound they are trying to scrub out of their antenna is the oldest thing in existence. It is the light of the Big Bang itself, 13.8 billion years old, arriving on schedule, refusing to leave. Two men on their knees cleaning the birth of the cosmos off the inside of a horn, certain that it is dirt. That happened, it was confirmed, it won a Nobel Prize. But to understand how the afterglow of creation got mistaken for a malfunction, and why that same faint signal has been falling into your living room your entire life, we have to go back. Back to a prediction made in 1948 and then ignored for 17 years. Back to a phone call from Princeton that opened with the words, "Boys, we have been scooped." Back to the moment, 380,000 years after the beginning, when the whole universe turned clear all at once. And then forward to the single flaw in that ancient light that is the only reason you are here to hear about it. Pour something warm and settle in, because by the time we finish, the static you have ignored your whole life will look like a photograph of your own origin. If you want these episodes with no ads, they live over on our Patreon, Meridian Labs, the membership behind this channel and a few others like it, with early access before each film goes public. Subscribe or join if you have not. Let's ease into it. For most of the last century, if you owned a television and you turned the dial to a channel that carried no station, you would see it. Grey and black flecks crawling over the glass, a restless swarming static with no pattern and no centre. The sound of it a flat hiss that seemed to come from nowhere and everywhere at once. Analog snow. You have seen it. Anyone who lived through those decades saw it, late at night, after the last broadcast ended, when the screen gave up on carrying a picture and showed you instead the raw noise underneath everything. And a small fraction of that snow, roughly one flicker in every 100, was not coming from a distant transmitter. It was not a loose cable or a fault in the electronics inside the set. It was coming from the edge of the observable universe. It was light that had been travelling toward that screen for 13.8 billion years. It was the oldest thing that has ever touched a human being, and it was falling into living rooms every single night, and not one person watching had the faintest idea what they were actually looking at. That light has a name now: the cosmic microwave background. It is the afterglow of the moment the universe first became clear enough to see through, and it fills all of space in every direction at every instant, including the space inside the room you are sitting in right now. There are about 411 photons from that first moment inside every cubic centimetre of the air in front of your face. They are passing through you as you read this. They have been falling on every human who has ever lived, on every animal, on every rock and ocean and cloud, since long before there were eyes to catch them. And for the entire span of human history, nobody knew they were there. Then, in the summer of 1964, two men found them. And here is the part of the story that I keep coming back to, the part that I think never gets told properly. They were not looking for the birth of the universe. They had no interest in cosmology. They were radio engineers with a very expensive antenna and a very specific technical problem, and the oldest light in existence showed up in their equipment as an irritating hiss they could not get rid of. And they spent the better part of a year trying to destroy it. They cleaned it. They rewired it. They climbed inside the antenna and scrubbed it out by hand. They were, without knowing it, two men standing at the beginning of time trying to sweep it under the rug. The two men were Arno Penzias and Robert Wilson, and they worked at Bell Telephone Laboratories at a facility on a low-rise called Crawford Hill in Holmdel, New Jersey. Bell Labs in that era was one of the strangest and most productive institutions that has ever existed. It was the research arm of the American telephone monopoly, which meant it was swimming in money and largely left alone, and it hired brilliant people and let them chase whatever they found interesting. The transistor was invented there. Information theory was invented there. The laser, the solar cell, the Unix operating system, all of it came out of the same handful of buildings in New Jersey. And sitting on Crawford Hill was a piece of equipment that looked less like a telescope than like an enormous metal ear laid on its side. A horn reflector antenna. 20 feet across at the mouth, about 6 meters, 50 feet long, weighing something close to 18 tons, mounted so that it could be tilted and swung to point at any part of the sky. It had not been built to look at the universe. It had been built to listen to balloons. In the late 1950s, the United States had launched a project called ECHO, which was one of those ideas that sounds made up, but was completely real. The plan was to put an enormous aluminized balloon into orbit, a shining metal sphere 100 feet wide, and bounce radio signals off it from one side of the country to the other. A passive satellite. A mirror in the sky. The horn on Crawford Hill was built to catch those faint bounced whispers coming back down from the balloon, which meant it had to be extraordinarily sensitive and extraordinarily good at ignoring everything it was not pointed at. And that second quality, the ability to ignore stray noise, is the thing that matters for this entire story. The horn was shaped so that almost nothing could leak into it from the ground or the sides. When you pointed it at a patch of empty sky, it heard that patch of sky and almost nothing else. It was one of the quietest instruments on the planet. By 1963, the balloon project was winding down and the horn was freed up for other work. Penzias and Wilson took it over. They wanted to use it for radio astronomy, to measure the faint radio glow coming off our own galaxy and other objects in the sky, and to do that with real precision they first had to do something that sounds boring and turned out to be the most important measurement of the 20th century. They had to find out exactly how much noise their own equipment was making. Every receiver has a hum. Every amplifier, every wire, every warm surface adds a little static of its own, and if you want to measure a faint signal from space, you have to know precisely how much of what you are hearing is the sky, and how much is just the machine talking to itself. Their plan was to point the horn at the emptiest, darkest, most featureless patch of sky they could find, somewhere with no bright radio sources, and measure whatever was left. They expected almost nothing. A whisper of noise from the atmosphere, a tiny contribution from the warm walls of the antenna. Together, by their calculations, it should have added up to a temperature of a little over 3 degrees above absolute zero, and most of that was accounted for, understood, boring. Radio engineers measure the strength of a signal in degrees. It is a convenient trick. Any warm object gives off radio noise, and the hotter it is, the louder the noise, so you can describe the strength of any radio signal by asking what temperature an object would have to be to produce that much hiss. When Penzias and Wilson pointed their horn at empty sky and added up everything they understood, they expected to hear a signal equivalent to roughly 3.3 degrees above absolute zero. What they heard instead was about 3.5 degrees higher than that. An extra glow. A persistent, faint, inexplicable warmth in the sky where there should have been nothing at all. Now, 3.5 degrees above absolute zero does not sound like much. Absolute zero is the coldest anything can be, minus 273.15 degrees on the Celsius scale, the temperature at which all motion stops. A signal 3.5 degrees above that is unimaginably cold and unimaginably faint, but it was there. It would not go away. And the fact that it would not go away, and the fact that they could not explain it. is the loose thread that, when they finally pulled it, unraveled the entire history of the universe. Here is what should have made it easy to dismiss, and what instead made it impossible. The excess was the same everywhere. They swung the horn to the north and the noise was there. They swung it to the south, the east, the west, and the noise was exactly the same. They came back in a different season, when the Earth had moved to the other side of its orbit and was pointing at a completely different part of the sky, and the noise had not changed. Day and night, it was identical. This is not how ordinary sources of radio noise behave. If the noise were coming from the galaxy, it would be strongest when they pointed at the bright band of the Milky Way and weakest when they pointed away from it. If it were coming from a city, from the sprawl of New York 50 miles to the north, it would be loud in one direction and quiet in the others. If it were coming from the sun, it would follow the sun across the sky. This noise did none of that. It was smeared perfectly evenly across the entire sky, as though the whole of space were glowing very faintly and very uniformly, and no source they could think of made any sense. I want to slow down here, because the strangeness of what they were dealing with is easy to skip past. They were hearing a sound with no direction. Every other thing in the sky has a location. Stars are somewhere. Galaxies are somewhere. Even the diffuse glow of our own galaxy has a shape, a structure, a place you can point to. But this had no place. It came from the whole sky at once, with the same intensity, as if it were not out there among the stars at all, but was instead a property of space itself. And that is a genuinely disorienting thing to measure, because everything in a scientist's training tells them that signals come from sources, and sources have positions, and a signal with no position must be an error. They assumed it was an error. They assumed the fault was in the machine. They were wrong about that, and the process of discovering how wrong they were took almost a full year. And it is one of the most quietly comic episodes in the history of science, involving pigeons, which we will get to. But the question they had stumbled into is not really the question you might think. It is easy to imagine that the mystery here is simply what was making the noise, and that once they figured that out, the story was over. It is not over, because the answer, the true answer, the one that took a phone call from a physicist 30 miles away to deliver, only opened a much larger and much stranger door. What Penzias and Wilson had accidentally recorded was a photograph. Not a photograph of a thing in the universe, a photograph of the universe itself, taken when it was newborn. An image of the entire cosmos at the age of about 380,000 years, which for a universe that is now 13.8 billion years old, is roughly the equivalent of a photograph taken a few hours after birth. It is the oldest image that can exist, and I mean that in a precise and unsettling way. It is not merely that we have not found anything older. It is that nothing older can ever be seen, by anyone, ever, no matter how good our instruments become. This light is a wall. It is the boundary of the visible, the edge of everything that can be looked at, and behind it the universe is permanently, structurally dark. When you look at the cosmic microwave background, you are looking at the last moment before the lights came on, and you are looking at it from the inside. That is the first thing that should sit strangely with you. But it is not the thing that keeps cosmologists awake. The thing that keeps them awake is that this photograph, this image of the infant universe, stretched across the entire sky, is smooth. Almost perfectly, almost impossibly smooth. The temperature of that ancient light is the same in every direction to about 1 part in 100,000. Point your instrument at one edge of the sky, then point it at the exact opposite edge, at a region so far away that light from it has only just now reached us after travelling since nearly the beginning of time, and the two regions have the same temperature to 5 decimal places. And they should not. There is no reason they should. Those two regions have never met. They have never exchanged light, or heat, or any signal of any kind. In the standard picture of the expanding universe, they have been separated by more than the age of the universe since the very beginning. Nothing has ever passed between them, and yet they agreed, in advance, to be exactly the same temperature. How does one side of the universe know what temperature the other side decided to be, when the two sides have never been in contact and never could have been? That question has a name. It is called the horizon problem, and it is not solved. There is a leading answer, a theory called inflation, and we will come to it. And you should know now that it is both the most successful and the least confirmed idea in modern cosmology, an explanation so strange that it proposes the entire visible universe was once smaller than a proton and expanded faster than light for a sliver of a second. But hold that. The point I want to plant, the thing to carry with you through everything that follows, is that the accidental discovery on Crawford Hill did not close a mystery. It opened the deepest one we have. The oldest light in existence is smooth in a way that our physics cannot fully account for. And the tiny, tiny places where it is not smooth, the flecks and imperfections at the level of 1 part in 100,000, turned out to be the seeds of every galaxy, every star, every planet. And every living thing, including the 2 men who spent a year trying to scrub that light out of a metal horn, and including you. We will build to all of it. But it starts with the noise, and the noise starts with 2 men who were absolutely certain their equipment was broken. Because the more carefully you look at what Penzias and Wilson actually did in that year, the clearer it becomes that the universe did not hand them this discovery. They fought it every step of the way. They did everything in their considerable power to make the birth of the universe go away, and its refusal to go away is the only reason we know it happened at all. To understand why these 2 men reacted to the birth of the universe by reaching for cleaning supplies, you have to understand who they were, because they were almost perfectly designed to distrust a signal like this. Arno Penzias was born in Munich on the 26th of April, 1933, which is a date that tells you a great deal before anything else is said. 1933 is the year Hitler came to power. Penzias was a Jewish child in the capital of the movement that intended to erase him. By the time he was 5 years old, the family had been marked for deportation to Poland, and in the days around the violence of Kristallnacht, his parents made the decision that saved his life. They put Arno and his younger brother Gunther on a train. It was one of the Kindertransport trains, the rescue operation that carried thousands of Jewish children out of Nazi Germany to Britain, most of them without their parents, many of them never to see their parents again. Arno was 6. He was told to look after his brother. He carried that instruction across a continent. His parents got out too, barely, and the family was reunited and eventually reached New York in early 1940, and Arno Penzias grew up in the Bronx, a refugee child who had learned before the age of 7 that the world could decide you did not belong in it, and that survival could depend on being sent away. He worked his way through the City College of New York, served as a radar officer in the army, and then did his doctorate at Columbia under Charles Townes, the man who invented the maser and the laser, and who would win his own Nobel Prize in 1964. Penzias came out of that training with a particular temperament. He was rigorous to the point of stubbornness. He did not trust things that could not be pinned down. A man who has learned young that comfortable assumptions can kill you does not casually accept that a mysterious warmth in the sky is the leftover heat of creation. He accepts that his equipment is dirty. Robert Wilson was almost his opposite in background and his match in rigor. Born in Houston, Texas, in 1936, the son of a man who worked in the oil fields, Wilson was quiet, methodical, mechanically gifted, the kind of person who liked to understand a machine down to its last screw. He studied at Rice and then took his doctorate at Caltech, where he learned radio astronomy from some of the best in the world and absorbed a deep instinct for calibration, for knowing exactly what your instrument is doing before you trust a word it tells you. Years later, reflecting on the whole affair, Wilson said something that I think is one of the truest things any scientist has ever said about discovery. He said that when an experiment goes wrong, it is usually the best thing, because the thing you did not expect to see is often much more important than the thing you were looking for. But in 1964, he did not yet know that his experiment had gone wonderfully, world-alteringly wrong. He just knew it had gone wrong. The two of them set out to find the source of the excess. And what follows is a methodical, almost obsessive elimination of every possibility, which is worth walking through in detail, because the thoroughness is the whole point. This was not two men glancing at a dial and shrugging. This was a year-long siege against their own ignorance. First, the cities. The largest source of stray radio noise on the ground is human civilization, and there was plenty of it nearby. New York City sat about 50 miles to the north, but the horn was so good at ignoring anything it was not pointed at, and the excess was so evenly spread across the sky that terrestrial interference was ruled out early. Cities are in a direction. This was not. Then, the galaxy. Our own Milky Way glows in radio, and if the excess were coming from the galaxy, it would brighten and dim as they scanned across the sky. It did not, and in any case the physics was wrong. The kind of radio glow the galaxy produces at other wavelengths would have been far too weak at the wavelength they were using, which was 7.35 centimeters, to explain what they were hearing. The galaxy was not the culprit. Then, the instrument itself, which is where their suspicion naturally landed hardest, because a rigorous engineer always suspects the machine first. They checked the amplifier. Their receiver used a maser, an exotic amplifier cooled with liquid helium to a temperature just above absolute zero, precisely so that it would add almost no noise of its own. They checked it and rechecked it. They built a device called a cold load, a reference source chilled with liquid helium to a known temperature, so that they could compare the sky directly against something whose warmth they understood exactly. The comparison held. The sky really was warmer than it should be. The machine was not lying. Then they went after the antenna itself, inch by inch. A horn like this is built from riveted aluminum panels, and every seam, every joint, every rivet is a place where the smooth metal is interrupted, and interruptions in metal can radiate. They took aluminum tape and taped over the riveted joints inside the throat of the horn to smooth out any noise the seams might be adding. It made no measurable difference. The warmth remained. And then there were the pigeons. At some point in their inspection of the inside of the horn, Penzias and Wilson discovered that a pair of pigeons had taken up residence in the narrow part of the antenna, up where it entered the warm cab that housed the equipment. The birds had been living in there, and they had coated the interior with droppings. Now, this was a real lead, and you can feel the hope in it. A warm coating on the inside of the antenna would radiate. Bird droppings packed onto the metal might absorb and re-emit exactly the kind of faint warmth they were measuring. This might be it. This might be the whole answer, sitting there in the form of pigeon mess. Here we arrive at a detail that has been retold thousands of times, and I want to correct it, because the corrected version is better, and because it is the kind of thing that separates the people who actually know this story from the people who have only heard it. The popular version says that Penzias, being a dry and precise man, referred to the pigeon droppings in his official report as a white dielectric material, a deadpan technical euphemism for bird excrement. It is a wonderful line. It appears in countless books and articles and videos, and there is no primary document in which it can be found. It is not in the paper. The phrase that actually survives, the one that is genuinely on the record, comes from Wilson himself in his Nobel Prize lecture years later, where he described the pigeons roosting in the horn and wrote that they had covered the inside with, in his words, a white material familiar to all city dwellers. That is the real line. The famous droll euphemism is very likely a later embellishment, a story that improved in the retelling until it hardened into fact. And I point this out not to be pedantic, but because it is a small lesson in exactly the thing this whole story is about. The clean, memorable version of events is often not the true one, and the true one is usually stranger and more human. Because here is what they actually did about the pigeons. And it is not a euphemism at all. It is a little bit brutal. They trapped the birds. They put them in a box and mailed them, alive, to another Bell Labs site further away, hoping to be rid of them. The pigeons, being pigeons and being famously good at finding their way home, flew straight back. And at that point, Penzias made a decision that he spoke about with visible discomfort decades later. In an interview near the end of his life, he explained, with the flat honesty of a man who had thought about it many times, that the only humane way to deal with the returning birds was to shoot them. And they did. They cleaned out the horn, they removed the droppings, they eliminated the birds, and they measured again, certain now that they had found and fixed the problem. The noise was still there. Cleaning the horn produced only the tiniest reduction. The warmth in the sky did not care about the pigeons. It did not care about the tape, or the rivets, or the amplifier, or the cold load, or the direction, or the season. Every single explanation that a competent engineer could generate had been generated and tested and discarded. And what were they left with? They were left with a signal that filled the entire sky evenly, that never changed, that came from no source they could identify, that survived every attempt to eliminate it. And that corresponded to a faint uniform warmth of about 3.5 degrees above absolute zero, soaked into the whole of space. They had, by this point, done something remarkable without realizing it. Through sheer stubborn refusal to accept an unexplained result, they had proven that the excess was real. Not an artifact, not a mistake, not a local contamination, a genuine physical property of the sky. The universe, they had established beyond doubt, is glowing. Very faintly, very coldly, but unmistakably, in every direction, all the time. What they had not done, what they could not do, was explain why. They were engineers who had just measured the most important number in cosmology, and they had no idea what it meant. They thought they had a broken experiment, and this is where the story would have stalled, possibly for years, a strange unexplained result written up cautiously and set aside. If not for the fact that 30 miles away at Princeton University, a completely different group of physicists had spent that same year working out, from pure theory, that this exact signal had to exist. They had predicted the warmth in the sky, they had calculated roughly how strong it should be, and they were, at that very moment, building an antenna of their own to go looking for it. They were weeks, maybe months, from finding it themselves. They just did not yet know that 2 engineers with a repurposed balloon detector had already been staring at it for a year, cleaning it, cursing it, trying to make it stop. The man at the centre of the Princeton group was Robert Dick, and he was one of those physicists who was frighteningly good at almost everything he touched. He was an experimentalist and a theorist at once, which is rare, and he had a gift for inventing the exact instrument needed to catch a signal nobody had ever caught. Years earlier, he had built a device now called the Dick radiometer, a clever kind of radio receiver that rapidly switches back and forth between the signal it wants to measure and a reference source, so that slow drifts and errors in the electronics cancel out, and a faint, steady signal can be pulled cleanly out of the noise. That invention is the reason precise radio measurements of the sky are possible at all. Remember it. It matters enormously for how this story ends, and for a particular injustice buried inside it. In the early 1960s, Dick had become interested in a big idea about the history of the universe. He favoured a picture in which the universe might oscillate, expanding and then collapsing, and then expanding again, bouncing through cycle after cycle, and he reasoned that if the universe had ever been squeezed down into an extremely hot, extremely dense state, whether at the true beginning or at the bottom of a previous bounce, that heat would have left a trace. A universe that hot would have been filled with intense radiation, a bath of high-energy light, and as the universe expanded and cooled over billions of years, that light would have stretched and cooled along with it. sliding down from searing gamma rays and visible light all the way into the faint cold hiss of microwaves. It would still be here, it would fill all of space, it would come from every direction at once, because it was not emitted by any object, but was left over from a time when the whole universe was the object. And it would correspond, Dick reasoned, to a temperature of just a few degrees above absolute zero. Read that description again, and notice that Dick, working from pure theory in his office at Princeton, had just described the exact signal that Penzias and Wilson were at that moment trying to scrub out of their antenna. A faint uniform microwave warmth, a few degrees above absolute zero, coming from every direction. A property of space itself rather than of any source within it. He did not know their signal existed. They did not know his prediction existed. The prediction and the measurement were sitting 30 miles apart, and neither group had any idea the other was there. Dick did what good scientists do. He assembled a team to go find it. He put a young theorist named Jim Peebles to work on the mathematics, calculating more precisely what the temperature of this relic radiation should be and what it would imply about the early universe. Peebles would go on to become one of the most important cosmologists of the century, a man who spent the next 50 years turning cosmology from speculation into a precise quantitative science, and who would finally receive his own Nobel Prize in 2019. And Dick put two experimentalists, Peter Roll and David Wilkinson, to work building a small radiometer on the roof of a building at Princeton to hunt for the signal. They were, in early 1965, a group of first-rate physicists who knew exactly what they were looking for, knew roughly how strong it should be, and were constructing the instrument to catch it. They were, in other words, about to make one of the great discoveries in the history of science, and they were about to lose it by a matter of weeks to a phone call. The connection came through a chain of conversations, the way these things often do. Penzias, still chewing on his inexplicable noise, mentioned it to another radio astronomer, who mentioned a recent talk by Peebles about relic radiation from a hot early universe, who suggested Penzias get in touch with the Princeton group. Penzias called Dick. And the moment of that phone call has become one of the small legends of physics, recounted afterward by the people who were in the room. Dick was having a lunch meeting with his team, the group that was building the antenna to find exactly this signal, when the phone rang. He took the call. On the other end, Penzias described the persistent excess noise, the 3.5 degrees, the perfect uniformity across the sky, the year of failed attempts to get rid of it. Dick listened. He asked a few sharp questions. Then he hung up the phone, turned to the young physicists sitting around him who had spent months preparing to be the first humans to detect the birth of the universe, and said, in the version that David Wilkinson remembered and repeated for the rest of his life, "Well, boys, we have been scooped." I find that scene almost unbearably poignant, and I want to sit in it for a moment before we move on, because it is easy to read past it as a charming anecdote. Put yourself in that room. You are Peter Roll or David Wilkinson. You have understood something profound about the universe, that it began in fire and left an ember, and you have done the hard, unglamorous work of building the machine to prove it, and you are close. You are so close, the instrument is nearly ready. And then your supervisor takes a phone call, and you learn that 30 miles away, two engineers who were not even looking, who thought the signal was a malfunction, who tried to shoot the pigeons out of it, have been sitting on your discovery for a year. There is no bitterness in the recorded accounts, which speaks well of everyone involved. But the physics establishment does not often let you see a moment where profound understanding and profound bad luck collide so cleanly, and this was one of them. The two groups behaved with unusual grace. They agreed to publish together, side by side, in the same issue of the same journal, so that the observation and its explanation would appear as companions. In the 1st of July 1965 issue of the Astrophysical Journal, two papers ran back to back. The first was by the Princeton group, Dick, Peebles, Roll and Wilkinson, titled Cosmic Blackbody Radiation, and it laid out the theory, the argument that this signal was the cooled remnant of a hot early universe. The second was by Penzias and Wilson, and its title is one of the great understatements in the history of science. They called it a measurement of excess antenna temperature at 4,080 megacycles per second. Not a measurement of the birth of the universe, not the discovery of the afterglow of creation, a measurement of excess antenna temperature. As dry and cautious a title as a person could invent, and the caution ran through the whole paper. Penzias and Wilson reported their measurement, the excess of about 3.5 degrees, the uniformity, the fact that it was isotropic and unpolarized and free from seasonal variation. And then, when it came to what it meant, they refused to claim the cosmology for themselves. They wrote only that a possible explanation for the observed excess noise temperature was the one given by Dick, Peebles, Roll, and Wilkinson in their companion letter. That was it. They had measured the oldest light in the universe, and in print they would go no further than to note that some Princeton theorists had a possible explanation. This was partly modesty and partly a kind of scientific self-protection. They were engineers reporting a measurement, and they did not want to stake a claim on a grand cosmological interpretation they had not derived and could not fully defend. But there is something almost funny about it in retrospect. The most important astronomical measurement of the century, announced with all the drama of a memo about a faulty connector. The wider world did not miss the significance the way the title tried to hide it. The story reached the front page of the New York Times on the 21st of May, 1965, under a headline announcing that signals implied a Big Bang universe. And that phrase, Big Bang, carries its own buried irony. Because it was coined as an insult. It came from Fred Hoyle, a brilliant and combative British astronomer who did not believe in a universe with a beginning at all. Hoyle championed the opposite view, the steady-state theory, which held that the universe had always existed and always would, unchanging on a large scale, with new matter continuously created in the gaps as it expanded so that it never thinned out and never aged. In this picture there was no beginning, no origin, no moment of creation. The universe simply always was. And in a radio broadcast in 1949, Hoyle, describing the rival theory he found so distasteful, referred to it dismissively as this Big Bang idea. He meant it as mockery. The name stuck and outlived him and became the accepted term for exactly the theory he spent his life fighting. Because that is what the discovery on Crawford Hill did. It ended a war. Through the 1950s and into the 1960s, cosmology had been a genuine two-horse race. On one side, the Big Bang, a universe with a hot, dense beginning that expanded and cooled. On the other, the steady state, an eternal universe with no origin. Both fit the one great fact everyone agreed on, that the universe is expanding, the galaxies flying apart. Both had serious, respected physicists defending them. There was no way to choose between them from the expansion alone. But the two theories made one sharply different prediction. A Big Bang universe, having started hot, should be filled with the cooled afterglow of that heat. A faint uniform bath of microwave radiation coming from every direction. A steady-state universe, eternal and never hot, should have no such thing. The relic radiation was the one clean test that could kill one theory and crown the other. And there it was. 3.5 degrees above absolute zero, uniform across the whole sky, exactly as a hot beginning demanded, and exactly as an eternal universe forbade. Wilson himself, who had actually leaned toward the steady-state theory in his own sympathies, understood immediately that the measurement he had helped make was a death blow to the very picture of the universe he had preferred. The signal did not care what anyone preferred. The universe had a beginning. It had been unimaginably hot. It had cooled for 13 billion years. And the last faint warmth of that beginning had been falling on the Earth the entire time, unnoticed, until it turned up as an irritating hiss in a machine built to talk to balloons. The two men who found it would receive the Nobel Prize in Physics in 1978 for the discovery of the cosmic microwave background radiation. But the story of who received that prize and who did not is where this begins to turn from a tale of lucky accident into something with a harder edge. Because Penzias and Wilson were not the first people to predict this radiation. They were not even the second. The prediction had been made, correctly, with a startlingly accurate estimate of the temperature, 17 years before the phone call to Dick. It had been published. And then, it had been forgotten so completely that the men who eventually found the signal, and the men who explained it, had never even heard of the people who called it first. To find the people who called it first, you have to go back to the 1940s, to a Russian émigré physicist named George Gamow, who was one of the most colourful characters the field has ever produced. Gamow had defected from the Soviet Union in the most Gamow way imaginable by attempting to paddle a kayak with his wife across the Black Sea to Turkey, a plan that failed, before he eventually got out through a scientific conference and never went back. He was enormous, loud, endlessly playful, a man who filled his serious physics papers with jokes, and who once cost himself a measure of credibility precisely because colleagues could not always tell when he was being serious. And in the 1940s, Gamow became obsessed with a genuinely deep question. Where did the chemical elements come from? Why is the universe made mostly of hydrogen and helium, with everything else in small traces? He suspected the answer lay in the first few minutes after the beginning, when the universe was hot and dense enough to fuse particles together, and he set out to work through the nuclear physics of that early inferno. Working with him was a graduate student named Ralph Alpher, and it was Alpher who did much of the hard, detailed calculation. The two of them worked out how, in the ferocious heat of the young universe, protons and neutrons could combine to build the lightest elements, and how the observed proportions of hydrogen and helium could emerge from that primordial cooking. It was serious, careful, important work, and it became the core of Alpher's doctoral thesis. When they published the central paper in 1948, Gamow, being Gamow, could not resist a joke. The two authors of the work were Alpher and Gamow, but Gamow added the name of his friend Hans Bethe in the middle, purely so that the author list would read Alpha, Bethe, Gamow, a pun on the first three letters of the Greek alphabet, Alpha, Beta, Gamma. The paper is known to this day as the Alpha Beta Gamma paper. It is a wonderful joke. It also, in a small way, buried the credit of the graduate student who had done the work under the fame of a punchline, and that pattern, of Alpha's contributions being obscured, would haunt his entire career. But the crucial thing for our story is what Alpha and another colleague, Robert Herman, did next. Having worked out the conditions in the early hot universe, they realized that this fireball would not simply cook elements and vanish. It would have been filled with intense radiation, and that radiation would still be around. As the universe expanded and cooled, the radiation would cool with it, stretching to longer and longer wavelengths, until in the present day it would survive as a faint bath of microwaves filling all of space. And they did something that the popular tellings of this story almost always leave out. They calculated its temperature. In 1948, Ralph Alpher and Robert Herman predicted that the universe should be filled with leftover radiation from its hot beginning at a temperature of about 5 degrees above absolute zero. 5 degrees. The measured value would turn out to be about 2.7. They were off by less than a factor of 2 in a prediction made from scratch. 17 years before anyone found the thing, about a signal nobody had ever detected, using the physics of a beginning that half the field did not even believe in. It is one of the most impressive theoretical predictions in the history of cosmology, and it landed in the literature and sank without a trace. Here's where the story stops being simply charming and starts to carry an ache, because the obvious question is, how does a correct, quantitative, published prediction of the most important discovery in modern cosmology get completely ignored for nearly 2 decades, so thoroughly that when the signal is finally found, the discoverers and the theorists who explain it have never even heard of the men who predicted it. This is not a conspiracy. Nobody suppressed Alpha and Herman. There was no committee, no rejection, no campaign against them. And in a way that makes it worse, because what happened to their prediction is the ordinary, bloodless way that important truths get lost, and it is far more common than suppression. Several things went wrong at once. The prediction was embedded inside work on the origin of the elements, and that work ran into a serious problem. It turned out you cannot build the heavy elements in the early universe the way Gamow hoped, because there are gaps in the ladder of nuclear masses that the primordial fireball cannot bridge. The heavy elements are actually forged in stars, a discovery made in large part by Fred Hoyle, the very man who coined the term Big Bang as an insult. And so the element building project that the temperature prediction was attached to came to look like a partial failure, and the radiation prediction got dragged down with it, treated as a footnote to an idea that had not fully worked. The baby went out with the bathwater. And the technology was not obviously there. In 1948, the idea of actually detecting a signal a few degrees above absolute zero, smeared faintly across the entire sky, seemed impractical to the point of hopeless. Alpha and Herman have said that they did ask around about whether such a thing might be measurable and were given little encouragement. Nobody built the instrument, because nobody quite believed the instrument could work, and so the prediction sat there as pure theory, unlinked to any experiment, in a field that did not yet take the hot early universe seriously as a testable science. Gamow's group dispersed. Alpha and Herman moved into industry. The prediction aged quietly in old journal pages, correct and unread. When Dick and Peebles at Princeton worked out, in the early 1960s, that a hot early universe should have left relic radiation, they were reinventing something that had already been done. They did not know. Peebles derived the prediction fresh, unaware that Alpha and Herman had gotten there 17 years earlier with a better number. It was only after everything unfolded, after the discovery, after the papers, that the earlier work resurfaced and people realized with some embarrassment that the whole thing had been foretold in 1948 and forgotten. Alpha and Herman were, understandably, wounded by it. They had predicted the cosmic microwave background, they had put a temperature on it, and the discovery was announced, celebrated, and eventually crowned with a Nobel Prize, with their names appearing, when they appeared at all, as a historical footnote. The pattern I want you to notice, because it repeats throughout the history of this field, is not villainy. It is neglect. The scientific establishment did not reject Alpha and Herman's prediction because it was wrong. It ignored it because it was inconvenient, because it was attached to a project that stumbled, because the tools to test it seemed absent, and because the field was not yet ready to believe that the origin of the universe was a thing you could measure rather than merely argue about. First, the prediction was seen as untestable, and so it was ignored. Then, when it was tested and confirmed, it was seen as obvious, and the credit flowed to the people holding the instruments. The one thing the prediction was never allowed to be, in its own time, was important. And the injustice did not end with Alpha and Herman. Return to Robert Dick, the man who took the phone call, the man who assembled the Princeton team, the man who invented the radiometer, the very instrument that Penzias and Wilson used to make their measurement, the switching receiver that made precise radio measurements of the sky possible, was Dick's invention. He predicted the radiation independently, he built the field's tools, he sent his students to find it, and he came within weeks of finding it himself. When the Nobel Prize was awarded in 1978, it went to Penzias and Wilson alone. Dick was not included. Neither was Peebles at that time, though Peebles would eventually get his own decades later. The prize can be shared among at most 3 people, and the committee chose the 2 who held the antenna over the men who told the world what the antenna was hearing. There are physicists who consider this one of the clearer injustices in the history of the prize, and it is hard to argue with them. Penzias and Wilson deserved it, They did the meticulous work, they proved the signal was real, they refused to let it go. But a discovery is not only the moment of measurement, it is also the understanding of what has been measured, and the understanding in this case belonged to other people, who watched the honour go elsewhere. I want to be careful here, because it would be easy to turn this into a simple story of heroes and victims, and it is not that. Everyone in this story behaved, on the whole, with decency. The Princeton group did not fight the joint publication. Penzias, to his great credit, spent years afterward making sure that Alpha and Hermann's forgotten prediction was remembered, giving talks about the history, insisting that the earlier work be acknowledged. The refugee child who had learned about being erased made a point of not letting others be erased. There is something quietly moving in that. But the structural fact remains, and it is the fact worth carrying forward. The people who first understood what the oldest light in the universe was, and predicted it, and calculated its temperature, are largely unknown outside the field, while the men who found it by accident and thought it was a malfunction are in the textbooks. That is not because anyone was cruel. It is because of how knowledge actually moves through human institutions, which is unevenly, unfairly, and with a strong bias toward whoever happens to be holding the evidence when the moment of proof arrives. But let me return to the light itself, because we have been talking about the people who predicted and found and fought over it, and we have not yet fully confronted what it actually is. And what it actually is turns out to be stranger than any of the human drama around it. I told you at the start that this is a photograph of the universe as an infant, and that it is a wall beyond which nothing can be seen. It is time to look directly at that wall and to understand why it exists, and to sit with the fact that the smooth, uniform glow those two engineers measured is hiding a problem that our best physics still cannot fully solve. Because the deeper you look into that first light, the less it behaves like an answer, and the more it behaves like a locked door with something enormous on the other side of it. Go back to the beginning, to the universe as it was in its first few 100,000 years, and you find a place that would not let you see across a room. In that era, everything was hotter than the surface of a star, and matter did not exist in the calm neutral form we know now. It was plasma, a searing fog of bare atomic nuclei and free electrons, protons and helium nuclei, and a swarm of loose electrons all moving at tremendous speed, too hot to settle into atoms. And a universe full of free electrons is opaque to light. This is the crucial fact. Light, which is to say photons, cannot travel freely through a sea of free electrons. It slams into them, scatters off, changes direction, gets absorbed and re-emitted over and over, so that a photon in the early universe could travel only the tiniest distance before colliding with an electron and being knocked onto a new path. The early universe glowed with light, but that light was trapped, ricocheting endlessly inside the fog, unable to travel in a straight line. If you had been there, and you could have survived, you would have seen a blinding, featureless uniform glow in every direction, like being inside a cloud lit from within, with no way to see any object, because the light could not carry an image across even the smallest gap. Then the universe expanded, and expansion cools things, and after about 380,000 years, the temperature drops to a critical threshold, around 3,000 degrees. And at that temperature, something changed all at once, across the entire universe, in what was on cosmic timescales a sudden event. The universe cooled just enough for the free electrons to be captured by the nuclei and bound into complete, neutral atoms, hydrogen and helium, calm and neutral for the first time. Physicists call this moment recombination, which is a slightly misleading name, because the electrons and nuclei had never been combined before, so nothing was recombining. It is one of those historical accidents of terminology that survives because everyone is used to it. But the name does not matter. What matters is what it did to light. The instant the free electrons were swept up into atoms, the fog cleared. With no more loose electrons to scatter off, the photons were suddenly free. they stopped ricocheting and began to travel in straight lines across the newly transparent universe unobstructed, and most of them have been travelling in straight lines ever since. The universe became clear. The lights, in a sense, came on, or rather, the light that had been trapped was finally released to fly free. And that release happened everywhere at once throughout all of space in the same brief cosmic moment. Every point in the universe became transparent together. And here is a detail that almost nobody pictures correctly, because the name we use for this light hides it. At the moment it broke free, the cosmic microwave background was not microwaves. The universe at recombination was at about 3,000 degrees, and something glowing at 3,000 degrees does not glow in microwaves. It glows in visible light, a dull orange-red, roughly the colour of the dim filament of an old incandescent bulb, or the surface of a cool red star. And at the instant the fog cleared, the entire universe, in every direction, at every point, was flooded with a soft red-orange glow, uniform and everywhere at once, like being suspended inside a furnace with no walls, or inside a sunset with no sun. The whole of space was luminous. If you had somehow been there to see it, there would have been no dark sky and no individual sources, just an even, warm reddish light filling everything, coming from all directions with equal brightness, because you would have been inside the last moment of the glowing fog. That light was visible. What turned it into microwaves is the expansion of the universe itself. Over the 13.8 billion years since recombination, space has stretched by a factor of about 1100. And as space stretched, it stretched the wavelength of that ancient light along with it. By the same factor, the light slid down the spectrum, from red-orange visible light, through the near-infrared, through the far-infrared, and finally down into the microwave band where we find it today, its effective temperature dropping from about 3,000 degrees to about 2.7 degrees above absolute zero along the way. The word microwave in cosmic microwave background is not a fact about the light. It is a fact about when we happen to be looking. A civilization that had existed a few billion years after the beginning would have found a cosmic infrared background. We find microwaves. A civilization far enough in the future will find a cosmic radio background, colder and fainter still. The light is the same light, only the stretch has changed. We are reading a sunset that has been pulled over 13 billion years, so far toward the red that it has fallen out of sight entirely and into the faint hum of a radio receiver, and there is more of it than you can easily imagine. We tend to think of the universe as mostly dark, mostly empty, with light being the rare and precious thing, the starlight scattered thinly across a black void. That picture is backwards. This ancient light is, by an enormous margin, the most abundant light in the universe. For every single atom of ordinary matter anywhere in the cosmos, every atom in every star and planet and cloud and body, there are roughly 1 billion photons of the cosmic microwave background, closer to 1.5 billion. The relic light outnumbers matter by 1 billion to 1. Space is not mostly empty of light. It is drenched in this faint cold glow, everywhere all the time, so thoroughly that the overwhelming majority of all the photons in the entire universe, and not starlight at all, have never come from any star, and are instead these ancient survivors of the fireball, still arriving, still filling every cubic centimetre of everything. When you look up at a dark night sky and see a few thousand stars scattered across the black, you are seeing the rarest kind of light in the universe against a background that is, in truth, saturated with the commonest kind, the afterglow, invisible to your eyes only because it has been stretched too far to see. That is the light Penzias and Wilson found. It is the light that broke free at recombination, 380,000 years after the beginning, and has been streaming through space for 13.8 billion years since. And now you can understand precisely why it is a wall. When you look out into space, you are looking back in time, because light takes time to reach you, and the farther away something is, the longer its light has been travelling and the further back you are seeing. Look at the sun and you see it as it was 8 minutes ago. Look at the nearest large galaxy and you see it as it was millions of years ago. Look far enough and you are seeing the universe as it was hundreds of millions, then billions of years ago. And if you keep looking farther, keep looking back, you eventually reach the moment of recombination itself, the moment the fog cleared. And you cannot see past it. Beyond that moment, looking further back, the universe is opaque. There is nothing to see, not because there was nothing there, but because light could not travel, and so no image from before that moment can ever reach you. The cosmic microwave background is the surface of that fog, seen from inside. Cosmologists call it the surface of last scattering, the place where those ancient photons scattered off an electron for the very last time before flying free toward us. It is a wall made of the last moment before the universe became clear, and it surrounds us completely in every direction. Because in every direction you look far enough, you eventually reach the era when everything was fog. Sit with the strangeness of that geometry for a moment, because it breaks the intuition people carry about the Big Bang. People tend to imagine the Big Bang as an explosion at a point, somewhere out there, from which everything flew outward, so that if you looked in the right direction you might see the site of it, off in the distance. That picture is wrong, and the microwave background is the proof that it is wrong. The oldest light does not come from one direction, it comes from every direction equally, because the hot dense beginning did not happen at a place, it happened everywhere. Every point in space was once part of that fireball, including the point where you are sitting. The surface of last scattering is not a distant location, it is a sphere around you, at the edge of what your light can reach, and every observer everywhere in the universe sits at the centre of their own such sphere. The beginning is not behind us in one direction, it is around us, in all directions, a horizon in time disguised as a horizon in space. And the light from that surface is not just any light, it is one of the most perfect examples of a particular kind of radiation that physics has ever encountered, and this is where the story picks up again, decades later, with a satellite and a measurement so clean it produced a standing ovation. When something glows, purely because it is warm, a piece of iron in a forge, the filament of a bulb. A star, it produces a very specific and very precise spread of colours, a signature curve of brightness across different wavelengths that depends only on its temperature and nothing else. Physicists call it blackbody radiation, and a perfect blackbody spectrum is a kind of fingerprint of pure thermal origin, a sign that light came from something in complete thermal equilibrium and not from any particular chemical or physical process. If the cosmic microwave background really was the cooled afterglow of a hot early universe, a universe that had been in near perfect thermal equilibrium, then it should have an almost flawless blackbody spectrum, cooled down now to just under 3 degrees above absolute zero. For decades this was hard to test properly from the ground, because the atmosphere gets in the way and absorbs much of the relevant radiation. In 1989, the American Space Agency launched a satellite called the Cosmic Background Explorer, known as COBE, built specifically to study this ancient light from above the atmosphere with unprecedented precision. One of its instruments was designed to measure the spectrum of the background radiation to test whether it truly had the perfect blackbody shape that a hot beginning demanded. The physicist John Mather led that effort, and in January of 1990, at a meeting of the American Astronomical Society, the results were presented. The measured spectrum of the cosmic microwave background matched the theoretical blackbody curve so exactly that the error bars, the little marks that showed the uncertainty in each measurement, were smaller than the width of the line drawn for the theory. The data points sat on the predicted curve so perfectly that you could not see any gap between measurement and prediction at all. It remains one of the most precise agreements between theory and observation in the history of science. The room, full of astronomers who understood exactly what they were looking at, gave it a standing ovation, they were applauding a graph. But the graph was the thermal fingerprint of the birth of the universe, measured to a precision that left no room for doubt, and they knew it. That measurement closed the case completely. Whatever lingering room there had been to doubt that the microwave background was truly the relic of a hot beginning evaporated. Nothing but a universe that had been in thermal equilibrium at enormous temperature and then expanded and cooled could produce a blackbody spectrum that perfect, filling all of space in every direction. The steady-state theory could not produce it. No alternative could produce it. The universe had a hot beginning, and here was its cooled light, carrying the flawless thermal signature of that origin across 13 billion years, and landing in the detectors of a satellite exactly as the theory said it must. But a flawless blackbody spectrum, perfect and smooth and identical in every direction, brings us straight back to the problem I planted earlier, the one that all the human drama has been circling. Because that perfection, that smoothness, that sameness in every direction is not comforting once you understand what it implies. It is the deepest unsolved problem in cosmology. The oldest light is too smooth. And to see why that is a crisis rather than a reassurance, you have to ask a question that sounds simple and turns out to have no easy answer at all. How did every part of the newborn universe come to have exactly the same temperature when the different parts had never met and never could have? Picture two tiny patches of the sky on exactly opposite sides. You point your instrument straight up and measure the temperature of the ancient light coming from one patch. Then you point straight down at the patch on the precise opposite side of the sky and measure that one. The light from each patch has been travelling towards you for 13.8 billion years. Each patch is, in the present day, something like 46 billion light years away from you, and the two patches are therefore separated from each other by more than 90 billion light years. And here is the fact that should stop you. In the entire history of the universe, no light, no heat, no signal of any kind has ever been able to travel from one of those patches to the other. They are, and always have been, beyond each other's reach. When the light you are measuring left those two patches, at recombination, the patches were already too far apart for anything to have crossed the gap between them in the time the universe had existed. They have never been in contact. They never could have been. As far as either patch is concerned, the other one might as well not exist, because no influence from one has ever had time to reach the other. And yet, they are the same temperature. Not roughly the same to about 1 part in 100,000. Two regions of the universe that have never exchanged anything, that sit outside each other's entire causal history, that could not have coordinated by any physical means, are matched in temperature to 5 decimal places. Think about what temperature actually is and why this is so hard to swallow. When two things reach the same temperature, it is because they have been in contact and have exchanged heat until they evened out. Put a hot cup of coffee in a cold room and wait, and eventually the coffee and the room reach the same temperature because heat flowed between them until it balanced. That is the only ordinary way things come to share a temperature. They touch, directly or through some intermediary, and they equalize. But the opposite sides of the observable universe have never touched. There was never any coffee and any room. There was never any flow of heat between these regions, because there was never time for heat to cross the distance. How did they end up matched? What evened them out? By every rule we understand about how thermal equilibrium is reached, they should be at random, unrelated temperatures, wildly different from patch to patch across the sky, because nothing ever connected them. Instead, the entire sky, in every direction, sits at the same temperature to a precision that would require the whole universe to have somehow agreed on a value in advance, before any part of it could have communicated with any other part. That is the horizon problem, and it is not a minor technical wrinkle. It is a direct contradiction between the smoothness we observe and the basic physics of how smoothness can arise. For a while it simply sat there as an embarrassment, a fact about the universe that the Big Bang model described but could not explain. The theory could tell you the light would be there and roughly how cool it would be, but it could not tell you why it was so uniform. The uniformity was just put in by hand, an unexplained initial condition, a brute fact you had to accept. Then, in 1980, a young physicist named Alan Guth proposed a fix so radical that it took years for the field to absorb it, and it remains 4 decades later, both the leading explanation and an unconfirmed hypothesis. The idea is called inflation, and what it proposes is this. In the first unimaginably small fraction of a second after the beginning, long before recombination, long before the first second was even over, the universe underwent a burst of expansion unlike anything before or since. Not the steady, gentle expansion we see today, an exponential runaway, a doubling and doubling and doubling of the size of space, in which the universe grew by a factor of at least 1 trillion, and possibly vastly more, in a span of time so short that the numbers stop meaning anything. The whole thing was over in something like 1/trillionth of a trillionth of a trillionth of a second. And the reason this solves the horizon problem is elegant once you see it. Before inflation, the region that would become our entire observable universe was not large at all. It was fantastically tiny, far smaller than a single proton, and a region that's small is small enough for its parts to have been in contact, to have exchanged heat, to have reached a common temperature the ordinary way, by touching and equalizing. Back when it was all packed into that minuscule volume. Then inflation seized that tiny already uniform patch and stretched it, violently and almost instantaneously, into something enormous, blowing it up until the parts that had once been in cozy contact were flung billions of light years apart. The uniformity was established when everything was small and connected. Then, inflation preserved that uniformity while tearing the regions apart, so that today we see patches on opposite sides of the sky at the same temperature, not because they ever communicated across the vast distance between them, but because they were once the same tiny equalized speck before being stretched to opposite ends of the visible cosmos. The two patches were, in the deepest sense, once touching. Inflation is the answer to how they got so far apart while staying so alike. I need to stop and make sure the strangeness of this proposal is not lost in how neatly it works, because inflation is one of the most bizarre ideas ever to be taken seriously by mainstream physics. It requires the universe to have expanded faster than the speed of light. This is allowed technically because it is space itself that expands, and the cosmic speed limit applies to objects moving through space, not to the stretching of space between them, but the mental image is still staggering, a universe ballooning outward faster than light could ever cross it. It requires a whole region of space to have been smaller than a proton, and to have contained everything we can now see. And it requires a driving force nobody has ever directly detected. A strange field with a peculiar kind of energy that pushed space apart with tremendous force, and then, just as suddenly, switched off, dumping its energy into the hot particles that became the fireball we have been talking about all along. This field has a name, the inflaton, and I want to be honest with you about its status. Nobody has found it. Nobody knows what it was. There are dozens of competing versions of inflation, with different fields and different behaviors, and physicists cannot yet tell you which one, if any, is correct. Inflation is not a detail that has been confirmed and filed away. It is a brilliant, sweeping, and still fundamentally unproven idea, propped up by how well it explains things it was not specifically designed to explain, and haunted by the fact that its central ingredient has never been seen. And I want to be fair to it, because the honest picture is more interesting than either cheerleading or dismissal. Inflation is not just a story that happens to fit. It made several specific predictions before the data came in, and those predictions have come true, which is precisely why it has become the leading theory rather than one idea among many. It predicted that the universe should be spatially flat, its geometry balanced exactly on the line between curving in on itself and curving open, and when the frozen sound in the ancient light was finally measured with precision, the universe turned out to be flat to within a fraction of a percent. It predicted that the fluctuations in that light should be very nearly the same strength on all scales, but not exactly, that there should be a slight specific imbalance, with the ripples a touch stronger on larger scales than on smaller ones. And when the Planck satellite measured that balance, it found exactly the small tilt that simple versions of inflation predicted, a number slightly but unmistakably less than the perfectly even value, about 0.965, where a featureless universe would have given exactly 1. That is a genuine, quantitative, non-trivial prediction, made in advance and confirmed. Inflation predicted the shape of the fluctuations, the way they should be distributed, the correlations they should show. And measurement after measurement has come back matching. Inflation sits in one of the strangest positions in all of physics. It keeps passing its exams. Its predictions about the flatness of space, the pattern of the fluctuations, the tilt of their strength across scales, have been confirmed to high precision, over and over, by exactly the ancient light we are talking about. And yet the thing itself, the field that supposedly drove it, has never been detected, and the one measurement that would show us inflation directly rather than through its after effects has never succeeded. It is a theory that has aced every written test while refusing, decade after decade, to show its face in person. There is, in principle, a way to catch it. If inflation really happened, that violent stretching of space should have produced ripples in space itself, gravitational waves, primordial ones, echoes of the most extreme event in cosmic history. And those gravitational waves, if they exist, should have left a faint, very specific, swirling pattern imprinted in the way the cosmic microwave background is polarized, a particular twist in the orientation of the ancient light that nothing else could easily produce. Finding that swirl would be as close to a direct fingerprint of inflation as we could ever hope to get. It would be a signal from the first trillionth of a second of existence, and the search for it has become one of the great quests in modern cosmology, which brings us to a cautionary episode that I think is one of the most honest and revealing things that has happened in this field in the last generation. In March of 2014, a team running an experiment at the South Pole called BICEP2 called a press conference and announced that they had found it. The swirl, the signature of primordial gravitational waves in the polarization of the ancient light, the direct evidence of inflation. The news went around the world. There was footage of one of the theorists whose work had predicted such a signal being told, on camera, that it had been detected and being moved nearly to tears. It was hailed as one of the great discoveries of the century, a Nobel surely on its way, a look directly at the birth of space and time. And then, over the following months, it fell apart. Other physicists pointed out that the swirling pattern the team had seen could be produced not only by primordial gravitational waves, but also by something far more mundane, dust in our own galaxy, tiny grains of aligned interstellar dust that polarize light in a similar way. A joint analysis with data from another satellite confirmed the deflating truth. The signal was consistent with galactic dust. There was no confirmed detection of inflation. The great announcement was withdrawn. I tell you this not to mock the BICEP2 team, who were serious scientists undone by a genuinely difficult measurement, but because it reveals exactly how much is still open here and how badly the field wants to close it. The smoothness of the oldest light points to inflation. Inflation is elegant, far-reaching, and widely believed. And it is still, as of today, unconfirmed, its central prediction unverified, its driving field unseen. Its most celebrated apparent detection retracted within a year. The deepest feature of the cosmic microwave background, its impossible uniformity, is explained by an idea that we cannot yet prove is true. The wall those two engineers found is smooth, and we still do not fully know why. But the wall is not perfectly smooth, And the places where it is not smooth are where this story finally comes home to you. The cosmic microwave background is smooth to about 1 part in 100,000, which means it is not perfectly smooth. There are variations, faint ones, regions that are very slightly warmer, and regions that are very slightly cooler. And the difference between the warmest and coolest spots is around 100,000th of the whole. To put that in human terms, imagine a still ocean where the difference between the highest ripple and the lowest trough across the entire surface was about the width of a hair. That is how flat this light is, and also how much it varies. The variations are almost nothing. But almost nothing turned out to be everything. Finding those variations was the other half of the COBE mission, and it was harder than measuring the spectrum, because the fluctuations are so small that they hide beneath the noise of any ordinary instrument. A second team, led by the physicist George Smoot, spent years coaxing the pattern of tiny temperature differences out of the satellite's data, mapping the whole sky, subtracting out everything else, our own galaxy, the motion of the Earth, the instrument's own hum, until what remained was the faint intrinsic ripple in the ancient light itself. And in April of 1992, they announced that they had found it. A map of the entire sky covered in a mottled pattern of infinitesimally warmer and cooler patches, the first image of the actual structure in the newborn universe. At the press conference announcing the result, Smoot reached for a way to convey what they had done, and said that if you were religious. It was like looking at God. The line was criticised by some as overheated, and it is the kind of thing scientists are usually trained not to say, but I understand the impulse completely. They were looking at the seeds of everything. Mather for the perfect spectrum, and Smoot for these fluctuations, would share the Nobel Prize in Physics in 2006, for the discovery of the blackbody form and the anisotropy of the cosmic microwave background. The anisotropy, the unevenness, the flaws. Because here is what those flaws are, and this is the point where the entire story stops being about ancient history and starts being about you, specifically, and the matter you are made of. The slightly denser regions in that early universe, the patches that show up as very slightly warmer spots in the map, were regions with very slightly stronger gravity. And gravity, given time, is relentless. A region that starts out just a hair denser than its surroundings pulls in matter a little more strongly, which makes it denser still, which makes its gravity stronger still, which pulls in more matter in a slow gravitational avalanche that runs for hundreds of millions of years. The slightly denser patches grew. They gathered gas. The gas collapsed and heated and ignited into the first stars. The stars clustered into the first galaxies. And the slightly less dense regions, the cooler spots on the map, gave up their matter to the denser ones and emptied out into the vast dark voids that lie between the galaxies today. Every galaxy, every cluster of galaxies, the entire cosmic web of luminous structure stretched across the universe, grew directly out of those 1 part in 100,000 fluctuations in the oldest light. The map that Smoot's team produced is not just a picture of the early universe. It is a blueprint of where everything would eventually be. It is a map of the future, drawn in temperature 380,000 years after the beginning. Follow that chain all the way down and it arrives at your own body. A slightly warmer spot on that map became, over billions of years, a region rich in galaxies. Within one of those galaxies, our own, generations of stars formed and died, and stars are where the heavier elements are made. The early universe produced almost nothing but hydrogen and helium. Every atom heavier than that, the carbon in your cells, the oxygen you are breathing, the nitrogen in your DNA, the calcium in your bones, the iron in your blood, was forged in the nuclear furnace of a star and then scattered into space when that star died, and then gathered into new stars and planets, including this one, including you. And the reason those stars existed at all, the reason there was ever a dense enough region for a star to form, traces directly back to a faint temperature fluctuation in the light that two engineers in New Jersey were trying to scrub out of a metal horn. You are the descendant of an imperfection in the cosmic microwave background. The flaws in the oldest light are the reason there is anything here at all, instead of a smooth, sterile, eternally featureless expanse of thinning gas. A perfectly smooth universe would have stayed empty forever. Nothing could have formed in it. It is precisely because the first light was not quite perfect that galaxies exist, that stars exist, that planets exist, that you exist to look back at the light and wonder where you came from. The universe is here because it was flawed, and so are you. I want to give that a moment to settle, because it inverts something we usually assume. We tend to think of flaws as failures, as the places where something went wrong, but the entire structure of the cosmos, and every living thing in it, is built out of the places where the early universe was not quite uniform. If inflation stretched a tiny equalized patch into the smooth sky we see, then the fluctuations on top of that smoothness came from something even stranger. In most versions of the theory, the seeds of every galaxy were originally quantum fluctuations. The tiny unavoidable jitter that quantum mechanics says must exist even in empty space, blown up by inflation from the subatomic scale to the scale of the cosmos, which would mean that the largest structures in existence, the galaxies and clusters and the great cosmic web, are the magnified ghosts of quantum uncertainty in the first instant of time. The map of the sky would be a photograph of quantum noise, stretched across creation, frozen into the distribution of everything. We are not certain this is right, because we are not certain inflation is right. But if it is, then the reason you are here is that the early universe could not hold perfectly still, because nothing at the quantum level ever can, and that irreducible trembling became the seeds of worlds. And the wall is not finished surprising us, because there are features in it that we still cannot explain, features that were not predicted and do not obviously fit. When the maps of the cosmic microwave background were refined, first by COBE, then by a satellite called WMAP, then by an even more precise European satellite called Planck, a handful of oddities showed up that have not gone away. There is a region of the sky, now called the cold spot, that is larger and colder than the statistics of the standard picture say it comfortably should be, a stretch of the ancient light that is anomalously dim in a way nobody has convincingly accounted for. And there is a stranger thing still, an apparent alignment in the largest scale features of the fluctuations, a pattern that seems to line up with the plane of our own solar system in a way that has no business happening, because the oldest light in the universe should know nothing whatsoever about the orientation of our little planetary system, which formed 9 billion years after that light was released. The alignment has been given a half-joking, half-uneasy name in the literature. It is called the axis of evil. It may be a statistical fluke, it may be a subtle error, it may be a real feature that our physics does not yet understand. What it is not, at present, is explained. The wall those engineers found is smoother than it should be in the ways we can account for, and stranger than it should be in the ways we cannot, and both the smoothness and the strangeness remain, decades after COBE, matters that physics has not closed. There is a further layer to those fluctuations, and it turns the cosmic microwave background from a photograph into something closer to a recording, because the patches of warmer and cooler light are not random static. They have a structure, a rhythm, a preferred scale, and that structure is the frozen imprint of sound, actual sound, pressure waves that were ringing through the universe before the fog cleared. Go back once more to the era before recombination, to the hot opaque plasma. That plasma was not sitting still. In the slightly denser seed regions, gravity was pulling matter inward, trying to make them collapse. But the plasma was full of light, and light exerts pressure, and as matter fell into a dense region and compressed, the pressure of the trapped photons pushed back out, and the region rebounded, and then gravity pulled it in again, and it oscillated. In and out, compression and rebound, over and over. These oscillations were pressure waves moving through the primordial fluid, which is to say they were sound waves, real ones, propagating through the substance of the early universe at more than half the speed of light. The whole cosmos was ringing, a vast, deep, opaque instrument, filled with sound too low for any ear, sound with a wavelength measured in hundreds of thousands of light years. The universe rang like a struck bell for its first 380,000 years, and then, at recombination, the fog cleared, the photons flew free, and the ringing stopped, because the pressure that had driven it vanished the moment the light decoupled from the matter. The sound waves were frozen where they stood. Wherever a wave had been caught at its moment of maximum compression, the plasma was slightly hotter and denser, and that shows up in the ancient light as a slightly warmer patch. Wherever a wave had been caught mid-rebound, the light is slightly cooler. The pattern of warm and cool spots across the sky is a snapshot of those frozen sound waves at the instant the universe went silent and transparent. When we map the fluctuations, we are looking at a photograph of the last sound the early universe ever made. This is not a poetic flourish. It is precise, quantitative physics, and it is one of the sharpest tools in all of science, because the exact sizes of those frozen waves depend, with exquisite sensitivity, on what the universe was made of and what shape it has. There is a characteristic scale to the ripples, a preferred size of patch, set by how far a sound wave could travel in the plasma before recombination froze it. And when you measure the apparent size of that characteristic scale on the sky, its precise angular width, you are effectively measuring the geometry of the universe itself, because the path the light took to reach you across billions of years depends on whether space is flat or curved. Measure the frozen sound and you can read off the shape of the cosmos. When this was done, first roughly by COBE, then with increasing precision by the WMAP satellite through the 2000s, and then to astonishing accuracy by the European Planck satellite, whose main results came in the 2010s, the answers that came out reshaped cosmology into a precise science. The pattern of the frozen sound waves told us that the universe is flat, its geometry balanced on a knife edge. To within a fraction of a percent. It told us the age of the universe with a precision no previous method could approach, about 13.8 billion years, refined by Planck to 13.79 billion. It told us how fast the universe is expanding, and it told us something that remains, to me, the single most humbling fact in modern science. The fact that the oldest light hands us with complete confidence and no explanation whatsoever. The relative heights of the peaks in the pattern of frozen sound reveal how much of each kind of matter the early universe contained, because ordinary matter and the mysterious invisible matter called dark matter push on the sound waves differently, and the answer that comes out of the ancient ringing is that the ordinary matter, the kind that makes up stars and planets and gas and dust and every atom in your body, is only about 5% of the total contents of the universe. About another 27% is dark matter, some form of matter that has mass and gravity but does not emit or absorb light, that we have never directly detected, whose nature is completely unknown. And the remaining 68% or so is dark energy, a still more mysterious thing, an energy woven into empty space itself that is pushing the expansion of the universe to accelerate, and whose nature is, if anything, even less understood than dark matter. Everything we have ever seen, every star mapped, every galaxy photographed, every object that has ever emitted or reflected a single photon, all of it together is about 5% of what is out there. The other 95% is dark, unidentified, and known to us mostly through its gravitational fingerprints, one of the clearest of which is written into the frozen sound of the cosmic microwave background. Consider what that means about the discovery those two engineers made. They found a faint hiss and thought their equipment was dirty. That hiss turned out to be the oldest light in the universe. That light turned out to carry, frozen into its faint unevenness, a recording of the last sound the young cosmos ever made. And that recording, decoded, told us that the universe is overwhelmingly composed of substances we cannot see, cannot identify, and do not understand. And that everything we have ever known is a thin luminous film of ordinary matter floating on a vast dark ocean of the unknown. The most precise measurement in the history of cosmology, drawn from the signal Penzias and Wilson tried to eliminate, is also the measurement that tells us most emphatically how little of the universe we actually comprehend. We mapped the wall to extraordinary precision, and the wall told us that we are strangers in our own universe, made of the rare visible 5%, surrounded by a darkness we have named but not explained. There is one more thing the oldest light tells us, and this time it is about you, and about the ground under your feet, and it is the kind of fact that sounds impossible until you see how simple it is. The cosmic microwave background is uneven in a second way, on top of the tiny fluctuations that became the galaxies, and this second unevenness is much larger and much plainer. When you map the temperature of the ancient light across the whole sky, you find that it is very slightly warmer in one particular direction, and very slightly cooler in the exact opposite direction, by about 1 part in 1,000, which is roughly 10 times larger than the intrinsic ripples we have been discussing. For a while, when this was first noticed, it looked like it might be a real feature of the early universe. It is not. It is a Doppler shift, the same effect that makes the pitch of a siren rise as it races toward you and drop as it speeds away. Only here it is applied to light rather than sound, and it is caused by us. We are moving. The Earth, the Sun, the whole galaxy, all of it is hurtling through space, and when you move through this bath of ancient light, the light you are moving into gets very slightly compressed and warmed, and the light you are leaving behind gets very slightly stretched and cooled. The warm spot in the sky is the direction we are going. The cool spot is what we are leaving behind, and from the size of that tilt, you can calculate exactly how fast we are moving, which is the part that stops me every time. Our sun is moving at about 370 kilometers per second relative to the ancient light. And when you add up the motion of the sun around the galaxy, and the motion of the galaxy itself, you find that our entire local group of galaxies is being carried through the universe at something like 600 kilometers per second toward a particular region of the sky, pulled by the gravity of distant, enormous concentrations of matter. This is a strange thing to be able to measure, because it feels like it should be forbidden. One of the deep lessons of Einstein was that there is no absolute rest, no special stationary frame against which all motion can be measured, no way to say you are truly standing still rather than merely moving at a steady pace. And that remains true. The cosmic microwave background does not break it, because the ancient light is a physical thing rather than empty space, the average rest frame of all the matter and radiation in the universe, a kind of cosmic standard against which our motion can be compared. But the effect is uncanny all the same. You are, at this moment, being carried through the cosmos at about 600 kilometers per second, and you cannot feel it, and you never will, and the only reason anyone on Earth knows it is happening is that the oldest light in existence is a fraction of a degree warmer in the direction we are all falling. The universe left a signpost written in temperature, and it points the way we are going. And then there is the crack. Because for all of that precision, for all the triumph of reading the age and the shape and the contents, and even our own velocity out of the frozen light, the cosmic microwave background has, in the last decade, opened a genuine crisis in physics, one that has refused to close and has only sharpened as the measurements have improved. It comes down to a single number, the rate at which the universe is expanding right now, and there are 2 ways to measure it, and they do not agree. The first way starts at the beginning. You take the ancient light, you read the frozen sound, you feed it through the standard model of cosmology, and you calculate what the expansion rate today must be. The answer that comes out is about 67, in the units cosmologists use, and it is known to a precision of about 1%. The second way starts here and now. You measure the actual expansion directly in the nearby universe by using pulsing stars and certain exploding stars that always flare with almost exactly the same true brightness to work out the distances to galaxies and how fast they are receding. The answer that comes out of that method is about 73, also known to about 1%. And those two numbers, 67 from the early universe and 73 from the local one, cannot both be right if our picture of the universe is complete. The gap between them is about 9%, and it has now reached a statistical significance that cosmologists describe as 5 sigma, meaning the odds that it is a mere fluke are less than 1 in 3 million. The obvious first suspicion is that somebody made a mistake, most likely in the local method, which leans on a long chain of assumptions about how bright certain stars truly are. Astronomers turned the James Webb Space Telescope, with its far sharper vision, onto exactly those stars to check whether the local measurement was contaminated by crowding or dust. In 2024 and 2025, the results came back, and they confirmed the local measurement rather than dissolving it. The hunt for a hidden error has so far deepened the disagreement instead of resolving it, which leaves the more unsettling possibility, the one that a growing number of physicists are being forced to take seriously, that both measurements are correct, and that the standard model of cosmology, the same model that reads so much so beautifully out of the ancient light, is missing something real between the early universe and now. Some new physics. A dark energy that changes over time, perhaps, a hint of which has turned up in recent surveys, though even that does not cleanly close the gap. As of the time of writing, nobody knows. The two most precise measurements of how fast the universe is expanding disagree. They have stubbornly refused to be reconciled, and the contradiction sits at the center of cosmology like a fracture that keeps widening. And notice where one side of that fracture comes from. The lower number, the 67, comes straight out of the oldest light, out of the frozen sound in the cosmic microwave background that two engineers tried to scrub out of a metal horn. That signal is now one of the two witnesses in the deepest unresolved argument in modern cosmology, and the two witnesses contradict each other. The wall handed us the most precise account of the universe we have ever had, and then, in the same breath, handed us a disagreement about the most basic fact of all, how fast everything is flying apart that our best physics cannot currently settle. This is the strange doubleness of the cosmic microwave background that I keep circling back to. It is the most informative single source in all of cosmology, the thing that turned the study of the universe's origin from philosophy into measurement, that killed the steady-state theory that dated the universe, that weighed the dark matter and revealed the dark energy that carries the frozen sound of the beginning and the seeds of every galaxy. And it is simultaneously a monument to how much remains hidden, a wall we cannot see past, smoothed by a process we cannot confirm, marked with anomalies we cannot explain. And encoding a universe that is almost entirely composed of things we cannot name, it answers more questions than any other object in the sky, and every answer it gives arrives holding a deeper question, which brings us, finally, back to the light itself, and to where it is right now, and to what it is doing as you sit here reading this. Right now, in the cubic centimetre of space just in front of your eyes, there are about 411 photons from the cosmic microwave background. In the volume of your body, there are millions of them at every instant. They are passing through the room, through the walls, through you, constantly from every direction, and they have been doing so your entire life. And they will continue after you are gone. Every one of them was released at the surface of last scattering, 380,000 years after the beginning when the fog cleared. Every one of them has been travelling in a nearly straight line ever since, for 13.8 billion years, crossing the entire history of the universe without hitting anything, until this moment. when it ends its journey by striking you, or the wall behind you, or the ground, and is absorbed, and ceases to exist as itself. Think about the life of a single one of those photons. It came into being as a flash of visible or infrared light in a universe that was orange hot and freshly transparent. A universe with no stars yet, no galaxies, no planets. Just a vast uniform glow beginning to fly free. It set out in some direction, and it travelled. While it travelled, the first stars ignited and died. Galaxies assembled. Our own galaxy formed. Somewhere along its path, about 9 billion years into its journey, a particular cloud of gas and dust in one spiral arm of one galaxy collapsed into a new star and a family of planets. And on the third of those planets, after another 4.5 billion years, oceans formed and life crawled out of them and eventually became things that could look up. And the photon, knowing none of this, kept travelling in a straight line at the speed of light for the entire span of it. And then, in the final instant of a 13.8 billion year journey, it reached the atmosphere of that third planet and passed through it and struck the retina of an eye, or the metal of an antenna, or the phosphor of a television screen, and died. The oldest light in the universe spends its whole existence in transit and ends it against us. We are, for a great many of these photons, the wall they finally hit. The last thing they ever do is arrive. And for decades, a small fraction of them arrived in living rooms, which is where this whole story began, with the static on an untuned television. That was real. When an old analog set was tuned to an empty channel and filled the screen with snow, roughly 1% or so of that snow, that restless swarming grey, was genuinely the cosmic microwave background. Ancient photons from the surface of last scattering striking the antenna and the electronics and adding their faint contribution to the noise. People sat in front of that, bored, waiting for a program to start, looking at the literal afterglow of the birth of the universe without the slightest idea, generation after generation. And then we switched to digital broadcasting, and the old analog snow vanished from our screens, and with it went that small accidental window onto creation that had been open in every home for half a century. It is a strange little elegy. For a while, without meaning to, we all had the oldest light in the universe flickering in the corner of the room, and then we upgraded and closed the window, and almost no one ever knew it had been open. I keep using the word wall for this light, and I want to be exact about what kind of wall it is, because it is not only a wall in space, it is a wall in knowledge, and it is permanent. When you look at the cosmic microwave background, you are looking as far back and as far away as it is physically possible to see, not with current technology, but ever by anyone with any instrument that could conceivably be built, because the universe before that moment was opaque, and no light from it can reach you. There is a hard edge to sight itself, and we are looking straight at it. Everything that happened before recombination, the first 380,000 years, including the beginning itself, including whatever inflation was, including the first instant, is behind that wall, and light will never carry an image of it to us. We can reason about what happened back there, we can build theories and test their consequences against the wall, and we have, but we cannot look. The cosmic microwave background is the last visible page of the universe's history, and every page before it is sealed shut, forever, by physics. The oldest thing you can see is also the end of seeing, and the wall is slowly fading. As the universe continues to expand, the cosmic microwave background continues to cool and stretch, its photons redshifting to ever longer wavelengths, ever fainter, ever colder. Right now it sits at 2.7 degrees above absolute zero, faint but detectable, well within the reach of our instruments. But it is dimming. Far in the future, hundreds of billions of years from now, the expansion will have stretched this light so far, cooled it so deeply, that it will fade below the point where any instrument could detect it against the noise of a colder and emptier universe. And the galaxies, too, will have been carried away from each other by the accelerating expansion until they vanish beyond the horizon of the visible. A civilization arising in that distant era, on some world around some late star, would look out and see only their own galaxy, alone in an apparently static void, with no cosmic microwave background, no evidence of expansion. No relic of a hot beginning. They would have no way to discover that the universe had an origin at all. The single most important clue to the history of everything, the clue that two engineers stumbled into in 1964, will have faded out of existence, and the truth of the Big Bang will become, for anyone in that far future, undiscoverable. We happen to live in the era when the evidence is still here. That is not guaranteed. It is a window, and it is open now, and it will not stay open. We are among the observers lucky enough to exist while the universe still remembers how it began, and still shows us, faintly in a signal that reads as static, the light of its own first morning. I want to come back to the people now, because the physics has given their story a weight it did not have when we started. Return to Arno Penzias, the boy who was put on a train out of Munich at the age of 6 because the country he was born in had decided he should not exist. He survived by being sent away. He was saved because his parents were willing to let him go. To push him out into the world alone with his little brother and the instruction to look after him, on the chance that being sent away was the only way to live. And then he grew up and became a scientist, and in 1964 he spent the better part of a year doing everything in his power to send away a faint persistent signal in his antenna, to get rid of it, to make it leave. Convinced it did not belong there, the signal turned out to be the oldest light in the universe, the afterglow of the moment everything began. The refugee child who was saved by being sent away spent a year trying to banish the birth of the cosmos, and became immortal in the history of science precisely because it refused to go. I do not want to make too much of the parallel, because a person's life is not a metaphor, and Penzias would probably have waved the comparison away. But it is there, and I find it hard to look away from. A man who knew, from the deepest and earliest part of his own life, what it costs to be told you do not belong, was the man who tried to tell the light of creation that it did not belong in his instrument. And when it turned out that the light did belong, that it was the most important thing anyone had ever measured, Penzias did something with the rest of his career that I think reveals his character more than the discovery itself. He made sure the forgotten were remembered. He went back into the history, found the 1948 prediction of Alpha and Herman that everyone had ignored, and spent years insisting, in talks and writings, that these men had called it first and deserved the credit that history had denied them. The child who had been nearly erased grew into a man who refused to let others be erased. He did not have to do this. It cost him nothing to let the standard story stand, the clean story in which he and Wilson simply discovered the background out of nowhere. He chose the harder, truer, more generous version. Penzias lived a long life, rose to lead the research at Bell Labs, and died in January of 2024 at the age of 90. Robert Wilson, the quiet Texan who leaned toward the steady-state theory and then helped kill it, spent his life in radio astronomy and lived to see the discovery he made by accident become the foundation of an entire science. His remark about the affair remains the wisest summary of it. When an experiment goes wrong, it is usually the best thing. Because the thing you were not looking for is often more important than the thing you were. And do not forget Robert Dick, who invented the instrument that made the measurement possible, who independently predicted the radiation, who assembled the team, who took the phone call, who said, "Boys, we have been scooped," and who then watched the Nobel Prize go to 2 other men without a word of public complaint. Or Alpha and Herman, who calculated the temperature of the afterglow 17 years before anyone found it, and lived most of their lives as footnotes to a discovery that was theirs first. Or George Gamow, the giant Russian who tried to kayak to freedom and who set the whole thing in motion with a joke about the Greek alphabet. Or Fred Hoyle, brilliant and wrong, who coined the name Big Bang as an insult and went to his grave in 2001, still refusing to believe in the beginning that his own mocking phrase had made famous. There is a whole crowd of human beings behind this signal, some vindicated, some overlooked, some honoured, some robbed, and the signal itself did not care about any of it. It simply arrived, as it had been arriving for 13 billion years, and waited to be understood. What strikes me most, looking at the whole arc of it, is how much of the greatest discovery in the history of cosmology was accidental, and how the accidents pile up until they almost start to look like something else. The antenna was built to talk to a balloon, and ended up hearing the beginning of time. The two men who found the signal were not looking for it, did not want it, and spent a year trying to eliminate it. The correct prediction had been made and forgotten so thoroughly that it had to be independently rediscovered. The connection between the measurement and its meaning came through a chance conversation and a phone call, weeks before a rival team would have found it deliberately. Remove any one of those accidents, and the story changes completely. And underneath all of them sits the deepest accident of all, the one without which none of the others could have happened, the one part in 100,000 imperfection in the smoothness of the early universe that allowed matter to clump and stars to form, and planets to condense, and life to arise, and eventually produced a species curious enough and equipped enough to catch the oldest light and ask where it came from. The universe is here because it was slightly flawed, and it is understood to whatever partial degree we understand it, because of a long chain of people who mostly were not trying to understand this particular thing at all. Consider where that leaves you, sitting wherever you are, inside a sphere of ancient light, because that is the true geometry of your situation, and it is worth holding clearly in your mind. You are at the centre of a shell of the oldest light in the universe, a surface of last scattering that surrounds you in every direction at the edge of the visible, and that light is not a distant abstraction. It is arriving at you continuously, from all sides, and it is the light released at the moment the matter that would eventually become you first settled into neutral atoms. The carbon and oxygen and iron in your body were not present at recombination. They were forged much later in stars, but the raw material was there, the hydrogen and the fluctuations. The slightly denser patch that would become the galaxy that would make the stars that would make your atoms. When you look at the cosmic microwave background, you are looking at the last coherent image of the state your own substance emerged from. It is not a photograph of some unrelated cosmic event. It is, in the most literal and least sentimental sense available, the closest thing to a photograph of your own origin that will ever exist, and it is the only one you will ever get, because there is no seeing past it, and you are still inside the event in a way that is easy to forget. The Big Bang is not something that happened far away and long ago and finished. You are in it. The expansion that began then is carrying the galaxies apart right now, this second. The light released then is falling on you right now, this second. The matter assembled from those fluctuations is your body right now, this second. There was no moment when the beginning ended and ordinary life began. It is all one continuous event, 13.8 billion years and counting, and you are a late, local, temporary knot in it. A place where some of the matter released from the fireball has arranged itself, briefly, into a pattern complicated enough to look back at the light it came from and feel something about it. You are the universe's afterglow becoming aware of the universe's afterglow, and the light that made that possible is still coming in, faint and cold and patient from the edge of everything, ending its 13 billion year journey against your skin without ceremony, the way it has ended against every living thing that has ever existed on this planet. For the entire span of human history, it fell on everyone, and nobody knew. It fell on the first humans who looked up at the night and made up stories about the lights, It fell on every civilization, every war, every ordinary afternoon, every person who ever lived and died, wondering where it all came from, with the answer pouring down on them silently the whole time. Unread, it fell on 2 engineers in New Jersey in the summer of 1964, and for the first time in the history of the species, someone noticed. And what they noticed, they mistook for a malfunction. They heard the birth of the universe and reached for a broom. They climbed inside the antenna and scrubbed the walls and trapped the pigeons and taped the rivets, doing everything a careful, rigorous, competent person does when the equipment seems to be broken. And the whole time the thing they were trying to clean away was the faint uniform glow of creation itself, 13 billion years old, arriving on schedule, refusing to leave. That is the part I cannot get out of my head. The oldest light in existence, the afterglow of the beginning, the single most important signal in the history of cosmology, the thing that dated the universe and weighed its darkness and carried the seeds of every galaxy, did not announce itself. It did not arrive with any sign of what it was. It showed up as noise, as static, as the kind of faint, irritating hiss that any engineer would assume was a flaw in the machine. The birth certificate of everything that exists is not kept in a vault or a temple or a laboratory. It is ambient. It is in the air of the room you are in. It was in the snow on every old television screen. It is falling on you as you read the last of these words. And it was falling on you before you knew it had a name, and it will keep falling long after, cooling and fading, until in some unimaginably distant era it slips below the reach of any instrument, and the universe forgets, at last, how to tell anyone how it began. 2 men tried to clean it out of an antenna. They could not. And the reason they could not is that there was nothing to clean. The noise was the universe, and it was doing the only thing it has ever done, which is arrive.